Thank you very much for the opportunity to speak here and the invitation. Yes, I'm an imposter. I happened to be in town and was invited kindly to come here, which I accepted. And I'm sorry not to be here for longer, as it looks to be a great conference. Michael Berry said he was intimidated because of me, but I am intimidated. I'm a mathematician talking about quantum mechanics to a group of distinguished physicists. So I'm the one who's really intimidated here, but maybe I can explain something of interest. So, and I apologize for not staying here for the whole week. So I'm going to have to leave early in the afternoon. Okay, so let me try explain what this is about. All right, so Michael gave a fantastic introduction to this. I will go over a few things that he was speaking about and leading to the situation in which we can say quite deep things using modern number theory. The connection to the Riemann hypothesis is, of course, something very inviting, and you're going to see a different connection. All right, so we have a Hamiltonian. I'm going to talk about the correspondence principle. I use X and C rather than generalized coordinates P and Q. We have Hamilton's equations, which I don't write down. You're all familiar with Hamilton's equations. And Hamilton's equations give a flow, and there's always one conserved quantity in Hamilton's equations. This is not time dependent, which is energy is fixed. But there could be other integrals of the motion, and on the energy equals fixed surface, will be, like Michael was talking, my configuration space is going to be compact so that we're going to have bound states when we quantize. There's a corresponding measure, which I'll always denote by d lambda. It's the central object in this talk. This is the invariant measure that is naturally there, and the question is, what other natural measures are there around that are connected with quantum mechanics? There are two extremes here. Michael also alluded to this. There's, before we quantize, I'm talking classical mechanics. Before we quantize, we could have H is completely integrable. So completely integrable is a notion that mathematicians love. Maybe people don't know this, but when Jacobi invented the Abel-Jacobi map to integrate the billiard ball or the geodesic flow on an ellipsoid, and he thought that was his greatest achievement, to use algebraic geometry to write down the integrals of the motion. So in the old days, solving Hamilton's equation meant integrating it with a full set of integrals. So the completely integrable case, we have the Hamiltonian itself as invariant for the equations, for Hamilton's equations. And then we have, if we in n degrees of freedom, we have another n integrals of the motion, which Poisson commute and globally are defined. There's tricky issues there. But those are the other integrals. And then the level set give us these invariant tori. And on the invariant tori, as Michael was describing, the linear motion in the action angle variable, the motion is linear. And that's, of course, the dream. You've solved the equation completely, straight line motion on a torus. At the other end, we have the notion of ergodic classical mechanics. That's where the system is almost every orbit's dense, but maybe there's some much more subtle chaotic features. But I will be really looking at the two extreme cases, in fact, only the second one, where we fully chaotic. And now chaos, when you define chaotic classical mechanics, there are many, many definitions. The example I'm going to look at is the most chaotic of all chaotic issues. So it's Benosov, it's K, it's Bernoulli, it's unstable orbits. Every periodic orbit is unstable. So we're really in the regime of purely, I'll call it fully chaotic, and I'm going to specify examples when we try to study the correspondence principle. All right, so it's 100 years ago. Before that was the old theory with periodic orbits, which, as was explained very nicely by Michael, Einstein pointed out some very important features that you could only quantize if you were completely integrable, because that was the only way that you could write down quantization rules in terms of these periods of these invariant tori. The semi-classical limit is, of course, I'm a mathematician. I don't put even h bar, because I once was giving a lecture like this and somebody said h bar is a number. What does it mean h bar goes to 0? Anyway, this is the semi-classical limit in the usual sense. And for the completely integrable case, as Michael explained, the Bohr-Sommerfeld theory of quantized invariant tori, clarified by Einstein, I would say they were doing some examples. Bohr was obviously able to quantize in his old theory hydrogen because it's completely integrable. Gives a complete understanding of the relation between the eigenvalues of the quantized system in the semi-classical limit, this correspondence principle, and how these eigenfunctions are localizing onto these invariant tori. Now, there are many contributors to this. It seems like we have the same set of, I had Berry, but he had Arnold. Maybe he didn't have Arnold, but he certainly had Keller and Maslow. But the person who wrote the most beautiful paper along these lines for me is Colin de Verdier, because he writes it in modern mathematical language of pseudo-differential operators, Fourier integral operators, which is the way I was brought up. And you can understand this principle of quantization and the semi-classical limit in the completely integrable setting. So I'm not going to discuss a completely integrable setting. We're interested in the chaotic setting where things are much, much more difficult. And this was the last discussion in Barry's talk. And I'm going to actually try give an answer to the questions that were asked. Now, as Barry said, if you think of random matrix theory, that usually means large, complicated random matrices. But the real interest in the subject here, which I learned today, is called quantum chaology, not quantum chaos, but call it whatever you want. What's in the name? The features that already appear already in the smallest numbers of degrees of freedom. So I'm going to stick to 2 degrees of freedom because that's the first time you can be non-integrable. And I will stick to even more special examples, which are mechanical systems, which are usually related to billiards, so that people have done numerics and we'll be able to look at the numerics and guess or glean from that what might be true. So 2 degrees of freedom, and rather than look at a general Hamiltonian, I'll look at something that's homogeneous, but it's sufficiently rich to capture every feature that we want. So X will be a compact Riemannian surface. So there's a Riemann surface and a Riemannian surface. A Riemann surface means a surface with a conformal structure or one-dimensional complex curve. And a Riemannian surface is a surface with a Riemannian metric. And the Riemannian metric gives me naturally a Hamiltonian. So I have a line element. I know you guys use summation convention. I write sum of ij, gij, positive definite line element. The dynamics for this is going to take place on the cotangent bundle of the surface. And because we're going to be preserving energy lengths of geodesics under the Hamiltonian, you'll see in a minute the unit cotangent bundle. Anyway, the Hamiltonian is given by Gij, Xi, Xj, where X's are the momentum or the tangent vectors. And if we have that as the Hamiltonian, then the Hamilton's equations become the equations for geodesic motion on this surface. So those are very beautiful Hamiltonian systems. You can think of them as you got this metric, you take a point and direction, that defines a geodesic, and you just follow that geodesic forever. It's going to wind around in this, the X is compact. The phase space, when you flow with the geodesic, the length of the geodesic remains constant. That's this energy level. So we, in a compact phase space, and we want to understand the classical mechanics and then the quantization. Now, whichever way you quantize, by the way, quantization, as far as I know, is not unique. I don't know how to quantize this. There's no canonical quantization here, but for the purposes that I'll be describing, I mean, if you're in Rn or if you're in some other situations, there are canonical Weyl quantization. But for the questions we'll ask here, one can actually prove that if you take a different quantization, the answer would be the same. So when I'm going to quantize the Hamiltonian itself here, I'm going to get the Laplacian for this metric, or sometimes called the Laplace-Beltrami. So the classical mechanics is the geodesic flow on this unit cotangent bundle. And the Laplacian in coordinates is written this way. It's the divergence of gradient. It's a second order operator And the most important thing I should have pointed out here as to why this is not special at all. What is special is the Hamiltonian is homogeneous in Xi. So I will be able to describe the semi-classical limit h bar, h goes to 0, as also equivalent to the eigenvalue gets large, and then I can forget about the number h, which I prefer to forget about. So in fact, I write the eigenvalue equation for the quantization, which is the Laplacian. I always use hat for quantization or op. That's a notation that's kind of reminds me what we're doing. So h goes to 0 is equivalent to the frequency of the eigenfunction going to infinity. So we have a very large frequency eigenfunction, and we want to understand the behavior of those states because we'll want to look at quantum observables and compare them with classical observables, and then try and understand the correspondence principle when the classical mechanics is chaotic. So that's what I define as quantum chaos, and we're going to try and answer those questions. So in various interpretations of quantum mechanics, you observe things. So classically, an observable here will be a smooth, I always take it to be a smooth function on the unit cotangent space. And if I look at a classical trajectory, so I'll evaluate this function on an orbit. So I start at some point V, I flow along gt here for some time t, and the first thing you would ask is what's the average of A on this orbit? Now, you might have a periodic orbit, you might have an orbit that's got a fractal dimension for its closure, and you might have a sort of generic orbit that's equidistributing with respect to the Liouville measure. And there's one nice theorem in the subject, which I want to explain before we get into the subtleties, and it's called quantum ergodicity. So let me first start off with classical ergodicity. So classically, you say a mechanical system is ergodic, Hamiltonian, or you can abstract it to a measure-preserving system. It's ergodic if they only, with respect to a measure, and the measure is the Liouville measure here, the one that we're highlighting all the time, if the only invariant sets, so now we get into measurable sets, the only invariant sets are either measure 0 or full measure. There could be invariant sets and very complicated ones of arbitrary Hausdorff dimension, and there will be. Yeah, that's exactly what classical chaos brings us. But the generic, the typical set in the set of measure, in the sense of measure, the only invariant sets are measure 0 or full measure. And in that case, the ergodic theorem of Birkhoff says that for almost all starting points in the sense of measure, the orbit, the observable A will be the average of A over the unit tangent bundle with respect to lambda. So almost every orbit will become dense and equidistributed. And that's soft, that's just the ergodic theory of the system, no chaos. All right, now if we quantize, how do we measure? I want to do the same thing at the quantum level. So we start with our observable A on the unit tangent bundle. That's a classical observable. And we quantize, we can quantize any classical symbol, and you would call it A at, I'll call it op A. For me, it's a differential operator now on this Hilbert space on which the miracle of quantization takes place. And its principal symbol is the symbol A, homogeneous of degree 0. That's exactly what all of you would do anyway, but it's mathematically rigorous, and I want to, everything I'm going to say here is rigorous and proved in the level of mathematics. There was some discussion of that at the end, and I'll say comments about that. So if we're looking, remember, at the semi-classical limit, which means large frequency, and if we look at op A, I want to look at the observable A in the state Cj. So in the standard interpretation, this is op A Cj in a product Cj, and that's what I would observe A to be in that state. That's the most important thing for me in this lecture, because I'm going to give you a deep interpretation of this in an arithmetic situation, very deep in terms of the Langlands program. You'll understand it, don't worry. Excuse me. This, many physicists call the Wigner function. Schnirelman introduced it. It's the micro-local lift, and you can think of it as a linear functional on the A's, which are on the unit, on this unit tangent bundle, but you can prove asymptotically this is a probability measure. There's an issue that it's not a probability measure before you take the limit. There's some issues there, but that's irrelevant for us. So this new J of A is a measure associated with the state, Cj, on the unit cotangent space. And the most interesting problem, the quantum mechanical problem that we want to understand is when the frequency, or in the semi-classical limit, what measures, what can you get? And so the space of measures has the property that it's pre-compact, and you can always take weak limits of measures in this situation. So you can always form the measure and then ask, what are they? So any measure which is a weak limit of these quantum observables will be called a quantum limit. And the big question is, what can that quantum limit? Can quantum mechanics see chaos? One question would be, could you get other limit measures here besides just the obvious limit measure, the Liouville limit measure? That's the most basic question. Now, there's a nice theorem that you can prove here. This was already observed by Schnirelman. It uses propagation of singularities. Once you're thinking of these bound states, there's nothing to stop you from using other functions of the Laplacian besides the Schrödinger equation. You could use the wave equation. So I actually come from the world of geometric optics, which is much more refined in terms of understanding singularities. And there's a theorem of Egorov on the propagation of singularities, which easily allows you to show that any weak limit of these measures will have at least one property. It will be invariant under the Hamiltonian flow. Now you might say, all right, well, that's game over. There's only one invariant measure under the Hamiltonian flow. That's the exact non-true fact. In the chaotic system, there's just a continuum of very complicated measures from unstable periodic orbits to singular measures. And could those come up as quantum limits? And that's the million-dollar question in a strongly chaotic case. All right, I want to just state this, and then I'll return to those pictures. So I want to state this beautiful theorem of Schnirelman, who stated it without giving a proof, and very few people were aware of it. It was stated in some obscure journal in the 70s when communications were not so good between the Soviet Union and the West. And when Colin de Verrier, excuse me, and Zeldich learned of it, they gave a proof, and Schnirelman's proof was written later. They're all the same proof eventually. But here is the only general theorem I know in terms of quantization, and it mirrors and reflects that if you have a classically ergodic system, there's an exact analog that there's a quantum mechanical ergodic theorem that goes with it, which we call quantum ergodicity. And this is what the theorem says, is let's take an observable A, G of t is our ergodic geodesic flow or Hamilton flow. This is very general, this theorem. And let me sum all the frequencies less than t. Now, the number of frequencies less than t, n of t, is something that Michael mentioned. It's called Weil's law. That we understand very well, and we're in dimension 2, so it's some constant times t squared, the way I've written it. So we know how many eigenvalues are less than or equal to t. Let's sum over all of those, the observables. I'm fixing A. I observe A in state Pj, and I subtract off the Liouville measure expectation, and I square that. So that's a variance calculation. And I sum the squares of those, t up to t. And these are basically bounded quantities. And the theorem that is true just under the classical, so if the classical mechanics is ergodic, then this, and this is not a trivial theorem by any means, but it's uses a lot of microlocal analysis. This sum is little o of n of t. So if I divide by n of t, it goes to 0. So that means, since these are positive quantities, almost all of these numbers, in the sense of density, must go to 0. And then by diagonalization argument, that's true for a dense set of A's, and that means that almost all quantum states become equidistributed if the classical mechanics is ergodic. So we're not talking about chaos there, this is just about ergodicity, but that must be kept in mind. It's exactly the question of if we are classically chaotic, can the quantum mechanics see the chaos? But here there's no chaos put in, so there's no chaos coming out. But almost all orbits are classically equidistributed, and almost all eigenstates, Wigner measures, are classically equidistributed. And that's the only general theorem I know in this subject, and it's a very important one. And so we want to understand this question. And this is from a paper of mine from maybe 12 years ago when there was a massive breakthrough that I'm going to describe. And the examples that you should think of, which illustrate everything I've been saying, is I told you that Jacobi was very happy that he integrated the geodesic motion on an ellipsoid using abelian integrals. If you take an ellipse, it's also completely integrable. The earliest reference I know of this is Boscovich, 1600. But this is a fact that the Greeks knew, that if you have a ellipse and a confocal ellipse, once tangent to a focal ellipse, always tangent to a focal ellipse, and you can go and prove that for yourself. For a circle, it's obvious, but for an ellipse, it's a little less obvious. There's a little theorem in projective geometry. So there's a second integral. So if I have an ellipse and I'm playing billiards and I'm solving the Dirichlet problem, this is my Hamiltonian, that's a completely integrable situation. And you see the WKB, or the concentration on invariant tori, dramatically. That's not a picture of the invariant torus, that's a picture of the eigenfunction's density. They are localizing on the invariant tori, and there's for each confocal ellipse, which has been suitably quantized, are exactly these localizing states. So this case we understand very well. A stadium is a little more complicated. Banimovic proved this was ergodic. This is quite difficult to prove is ergodic, and it was a very beautiful example. But the stadium has these bouncing ball modes, and it's not surprising that you won't have so there are going to be quantum limits which are supported on just on these bouncing ball trajectories. But otherwise, you see Schnirelman's theorem in action. Almost all of these, these two are, okay, almost all, 2 out of 12. But when in the limit, these unusual ones are 0 frequency. So you see the stadium I'll keep away because it's not purely chaotic. The most important numerics, as far as I'm concerned, because I'm going to tell you what I believe is true in general, but what is true in the number theoretic world will become clear, because those will be theorems. But in general, to test these, somebody has to do some really detailed numerics, and Alex Barnett from the Flatiron did some fantastic experiments, not with a Sinai stadium, but this kind of stadium where there's no bouncing balls, for which he's got code to compute many, many eigenfunctions and eigenvalues and can see where they localize. And the kind of picture that you see, and this is what you should be looking at, are these enhancements on some kind of periodic orbits. You see it a little bit here. Do those survive the semi-classical limit, or are they just some transient phenomena? That's the big question. And so in this is the picture we want to understand. And the case that we're going to study, you'll see why in a minute, is a hyperbolic region, like a hyperbolic triangle. If you take a triangle in the hyperbolic plane, the billiard ball in there is very chaotic. So I'm going to review this. This is the first mechanical systems that were shown to be chaotic, of the most full, every feature that you want in terms of exponents and so on. This happens to be the modular group, and that's going to be the connection to arithmetic in a second. You see the Riemann zeta function there. We won't be talking about it. We'll be talking about its relatives. Those are the nodal domains for these modular eigenfunctions of high frequency, for which there are beautiful conjectures of Berry, and for which a lot of them are now proved in the arithmetic situation. All right. So I've described quantum ergodicity, and now I describe the setting in which the arithmetic comes in. So far that was just the background. I just repeated the setup. And we don't want to talk about the integrable case, except I will say one word about the integrable case to show you that arithmetic is still there in some of Berry's conjectures. And these questions are extremely hard. If you think arithmetic is easy, well, I can tell you from experience, I don't know much about most of the problems that come up this way. So it's very interesting when the problem that comes up is sort of a central one from another point of view. So the setting in which we're going to have these geodesic flows be fully chaotic are those where the surface is of constant negative curvature -1, or at least variable negative curvature. You could allow that, but let's take constant curvature. And in that case, the surface can be realized in terms of hyperbolic surfaces. So the surface locally is a hyperbolic plane. The hyperbolic plane has this line element. And because it's locally like that, and then a little bit of topology, it's a quotient of the hyperbolic plane, just like you have a flat torus coming from an ordinary torus by dividing by a lattice. Here you divide by a discrete subgroup of SL2R. And that discrete subgroup, they come in families. They're going to play a big role here. So, sorry. In this case, the unit tangent bundle, and this is going to be important to us, the set of points and directions on the surface can be identified with the group SL2R over gamma. That's easy to check. And that'll be convenient because I'm going to bring in some more representation theory and group theory in order to describe the problem and its solution. The geodesic flow, which is our Hamiltonian flow, takes a coset. So I'm looking at this quotient. So if you take a coset G times gamma and you just flow diagonally by e to the minus t, e to the t over 2, that's the geodesic flow, and it's winding around in some very Anosov chaotic way. These are purely fully chaotic Hamiltonians. All right. Now, based on some results that I'm going to tell you, and early results of Rudnick and myself that we proved. In fact, the reason I got into the subject, it's because of Michael Berry here. There were some claims that were brought to me that in these settings, there are something called scars. And it was clear to me that if they're scars, why haven't we not seen them ourselves? Because these are objects I'm going to explain to you we work with all the time. So if there was some way that things want to localize on unusual sets on periodic orbits, we should be able to see this from the point of view of modern number theory. And we quickly realized that they don't exist. And there was a lot of debate. We went against the grain. Anyway, soon we made this conjecture, and now it's survived and even been proved in many cases. And that is that the only quantum limit in a fully chaotic system like this is the Liouville measure. You can never see anything else. You really have suppression of chaos at the full level. So the only quantum limit, so if you think there's a periodic orbit unstable, it will somehow have a funny subsequence of eigenstates that will pick that up, or some feature of that. The answer is no. There's only one possible answer, and I'm going to tell you why I'm so confident about that. And in fact, that there's a very good reason for it once you look at it the right way. So that's the conjecture of Rudnick and myself, and we even made it in fully chaotic systems of, let's say, Riemannian manifolds of negative curvature, all of which are Anosov and have all the features that we think are suppress the seeing of any chaotic features in once you've quantized. All right, I'll return to this decomposition of the regular representation. But let me just review something that Michael said. And the reason I want to review that is I want to point out that arithmetic comes in all these problems if you look at specific examples. So Michael already pointed out this rather beautiful statement, which is true typically, but what typically means is a big debate, but is not always true. And that is that if you quantize a classically completely integrable system, then the spectrum, the local spacing statistics should be Poissonian. And but surprisingly, that the eigenvalues are random in that case. On the other hand, if you quantize a classically chaotic system, it's a conjecture of Bohigas, Giannani, and Schmidt. All of these are based on numerics, is that the local spacings should be GOE. Neither of those are true, but they're probably true if you jiggle a little bit. And that's a very good picture to keep in mind. And there's no case of this where anything has ever been proved. Nothing at the local spacing level. And the reason these problems are very hard, and let's take the case that Michael already put down earlier today, and that's the example of a rectangle. That's the simplest case of an invariant torus. with Dirichlet boundary conditions. You're playing billiards in this, it's completely integrable. The integral of the motion is the angle. You always go at the same angle. And you can, of course, solve this explicitly. I want to emphasize the whole point about the chaotic system is people think you can write down the eigenfunctions explicitly. No. They are automorphic forms. They are objects of deep study in the case that I'll be talking about. So you can write them down here because of, we know the exponential function, and so the eigenvalues are m squared plus a n squared, where a is this number here. So if one side is 1 and the other side is a. Now, if a is an integer, this is number theory, that's easy to understand, but if a is root 2, and I ask, what's the local spacings? Look at the numbers m squared plus root 2 n squared, where m is greater than 1 and n is greater than 1. The number of numbers up to a number t is about t. Constant times t, as you usually can check. And then if you try to compute the local spacing statistics, Barry showed you a picture of that, perfectly Poisson. He said that Sinai misnamed something. Actually, Sinai does not believe this conjecture. In case he tried to prove it and then decided it can't be true, the numerics are misleading. I believe it's true, but anyway, this is an elementary number theory question. What are the spacings between, what are the local spacing statistics between m squared plus root 2 times n squared as you go? And his conjecture is that that's perfectly Poisson. And to show you how difficult it is, even the case of the pair correlation, which would be the differences between these numbers, which would be the first statistic you could compute, was only solved using the full force of homogeneous dynamics and Ratner's rigidity work, and foreseen by Raghunathan, actually, from India. And that is that if you take a quadratic form in 4-variable, which is indefinite, which would be the difference for the pair correlation, you can prove that you get the right number in any interval, and the pair correlation is Poissonian. So I've given you a little hint that maybe homogeneous dynamics might play a role somewhere, and it's going to play a decisive role in the chaotic case. This is the integrable case. All right, so when we look at these constant curvature hyperbolic surfaces, they come in 2 types. The first type are called arithmetic, and those are the ones which are number theoretic. So for example, the one that I drew for you, gamma equals a 2x2 integer matrices of determinant 1, you see the definition of the group involves whole numbers, and that's the word arithmetic. But the definition need not be whole numbers in the ordinary sense. They could be whole numbers in some algebraic number field. So the notion of arithmetic is much more subtle, and it's very important to capture the general one. And the 2 examples you might keep in mind are the case that is the modular group, which you would be playing billiards on this triangle. Now, this triangle's got finite area in a hyperbolic plane. It's got 0 angle at infinity. The area is pi minus the sum of the angles. It's got finite area, something you can't have in Euclidean space. So it's finite area. So the spectrum has got some continuous spectrum that we understand well. Just ignore that, where you could just put Dirichlet boundary conditions on the boundary of this and study the billiards inside here. And the quantization, of course, is the usual Laplacian Hamiltonian. Now, these arithmetic, this example here is the Hurwitz triangle group, my favorite arithmetic triangle group. Angle pi over 2, pi over 3, and pi over 7. There is something going on here that is going to be very important, and it's the source of us being able to say something and get around some difficulty. And there's a difficulty here. Maybe the eigenvalues are multiple. And if the eigenvalues are multiple, now I'm going to tell you a theorem that something always happens. How did I overcome that? So it turns out, and every physicist does this, if there are operators which commute with your operator, you should, A, know about it. Geometric operators. Of course, if you diagonalize, then you know who commutes. But suppose I set up the problem directly and I tell you who commutes with the Laplacian, and I give you a definition of some theory of correspondences, some geometric things that commute. So it turns out there's a definition of arithmetic. There are no symmetries of these things to talk of, but if you take the curve, the surface cross itself, this Riemannian surface, which is arithmetic, cross itself some number of times, and you look at the symmetric product, there are correspondences, there are maps from the surface into this product, into the symmetric product, which are locally isometries. So phi1 of z up to phi n of z are locally moving asymmetrically, but they're not defined globally except in the symmetric product as a multi-valued set. And these exist in every arithmetic case coming from number theory, these symmetries. And then if you average your function over these symmetries, because those are local isometries, you'll get an operator which will commute with your Hamiltonian. And these operators commute with each other, and this are called the Hecke operators. And I'm emphasizing this because we're getting to the point where our bound states that we want to say in terms of quantization are all of a sudden becoming objects that we study for a very good reason, because they are the basis of the Langlands program. And so it should be that the question of whether you can localize or not should have a meaning in terms of our theory, and the answer is absolutely. Okay, so we will always assume that if you're arithmetic, that you are you simultaneously diagonalize everybody. So whenever I talk about an eigenfunction, it's a simultaneous eigenfunction. When you're non-arithmetic, then there's no such operators. Now, there's a fellow Bogomolny whose name keeps on coming up in Michael's talk and came up already in my talk. And he invented, without knowing the notion of what an arithmetic group is, he came up with a definition that he could reconstruct it from scratch, because I've been taught it. So he was doing numerics with Schmidt, his collaborator who does all the numerics on these things, and they were taking hyperbolic triangles and checking if the spectrum is GOE as they expected. And everything was GOE as they happened. And all of a sudden there were 3 or 4 triangles for which it was Poissonian. Out of the blue, the complete wrong distribution. And it turned out that those are exactly arithmetic triangles, and it's not proved. But you could imagine that the fact that there's a big commuting family of operators is the source of making the eigenvalues more like random numbers than like random eigenvalues. Anyway, those are observational facts which show that the arithmetic and the non-arithmetic are different. But what I want to tell you is with respect to the eigenfunction, they're not different. The question of quantization and whether you see chaos does not seem to be different in these situations. All right, now the most important slide in this is this slide. It's the marriage between the quantum observable and the theory, modern theory of L functions. So this was first observed by Zeldich and myself. We were discussing this many years ago, and then it became an industry. Luo and I wrote papers. Rudnick and I led to this. My student, Tom Watson, proved this most important formula. And what this formula says is if you take observable on your unit tangent space of mean 0, so I'm already removed the mean, and I assume it's a Hecke eigenform itself. So I'm now doing something strange. I'm making the observable a Hecke eigenform, but they're dense, so if I understand them, I understand everything. Then the quantum observable of A, op A phi j absolute squared, is another value. It's the central value of an automorphic Langlands L function associated with these 3 automorphic forms. So let me emphasize, once we are a Hecke eigenform in this arithmetic situation, these objects, these eigenfunctions of H hat are the building blocks of modern automorphic forms. They are quite mysterious. We're trying to understand them. They all come with L functions. For someone who's interested in the Riemann zeta function, he knows I'm interested in that. If you want to know what all the L functions in the world are, they only come from these constructions. Langlands construction is the only one, and we believe it's a theorem basically. Those are the only ways you can construct L functions. So each one of these L functions comes with the Riemann hypothesis, and the Riemann hypothesis for this L function is decisive in this problem. It tells us everything. So at that point, you know that this question that we're asking about the quantum observable, is it going to equidistribute? The answer is not only will it equidistribute, but if I know the Riemann hypothesis for this L function, and so if I'm worried about the truth, he seemed to worry a little bit about the truth. I'm looking at all L functions. It's hard for us to imagine that The Riemann would be true for some and not others. Anyway, I'm going to give you unconditional theorems, but this is the key relation. And let me emphasize, it's the value of this L function at the center. So the Riemann hypothesis says all the zeros of whatever this function is on the line and a half, it's allowed to vanish at the center. And that has a very big meaning in terms of quantization. So it could vanish there, and that will have a meaning in a second. But the question of how big that is, because we want to know, do these quantum measurements op A, phi j, do they go to zero and at some exact rate? And the answer is yes. So the functional equation is always S into 1 minus S. It's a central point. And so the Riemann hypothesis for these L functions, and this is really, this is already telling us a tremendous amount, says that if A has mean 0, then op A phi j squared decays like Tj to the minus 1. And that is the rate at which the generic guy also decays. So I told you that Barnett checked this other setting of a Sinai billiard which had no symmetries, and there were no exceptions to this. This is, when you quantize a chaotic system, it does not want to allow you to have any limit except the level measure, and even at this God-given rate. And in this case, that's the rate that will happen if you know this remarkable Riemann hypothesis, but we don't. In any event, this is the exact fastest decay rate, and it agrees with Barnett. All right, so I want to show you what we can prove unconditionally, because I am a mathematician, so we prize unconditional proofs much more than even insights, which some physicists can't understand. I mean, a long, complicated proof that nobody understands is more important than an insight which everybody understands. Of course, the ideal world is a proof that everybody understands and really understands why it's true. Okay, we don't know how to prove Riemann, and when I tell you what we can prove here, so I want to explain that there is a theorem we can prove here, and a number of theorems using this connection unconditionally. And that's the analog of the quantum variance, of the classical variance. So the classical variance, if I look at these chaotic systems that we're looking at, and I fix a typical point V, and I look at the observable A along this trajectory, I integrate from 0 to t, and I divide by root t, not by t. The average converge to the integral. I'm assuming the integral is 0. Then this becomes a Gaussian in this setting, because it's a very chaotic system. This is a theorem of Marino-Ratner also. This becomes a Gaussian with some classical variance. The classical variance, even its definition, it's got an integral here. The reason this converges, this integral from minus infinity to infinity, it's a quadratic form in A on the unitangent, mean zero unitangent bundle. The fact that this converges is because of the mixing, these classical mechanics mix very quickly, exponentially, so this actually converges easily. And so you could ask, what about the quantum variance? And the quantum variance has exactly the same feature, and this is a theorem that Luo and I proved a special case, and much more recently Zhao and I, and then very, very recently the most general case was proved by Nelson. This is using all special techniques in the theory of automorphic forms. Anyway, the moral of the story is that you divide by square root of n of t, and this tells you that the decay rate that I was telling you about of quantum observables is sharp on average, and it converges to what we call the quantum variance. And the quantum variance is trying its best to be the classical variance. They both diagonalized by the action of G on this unit tangent bundle, and when you decompose this action into infinite dimensional irreducibles, the restriction of the quantum variance is the classical variance, except there may be a correction factor, and this correction factor is related to an L function possibly vanishing at a half. And that not for parity, for parity reasons. L functions can vanish for very deep reasons in algebraic geometry, and that happens here. And in that situation, all the quantum variances would vanish without you being able to explain, other than some deep arithmetic reason. So it really captures the essence of this quantum variance in this situation. All right, I think I have 10 minutes, or is that right? 5. Okay, because now I'm going to tell you a series of 3 beautiful theorems which are purely unconditional and do not use this. They use this plus other methods. So it turns out that I had tried, and many people have tried since, to prove this. You don't need to prove the full Riemann hypothesis to get this estimate. You just need to prove something called subconvexity. A big industry in the subject about estimating central values of automorphic L functions. But this has eluded all of us. And this would be the most interesting one to prove, because it would give you this equidistribution with a rate. But there are other approaches, and I want to tell you an approach which uses homogeneous dynamics, and that's this theorem of Elonland and Strauss from about, well, it's already quite a few years ago. So he proved unconditionally that in this arithmetic situation, the only quantum limit is Liouville. So that's it. That answers the question at this crudest level. The only suppression of chaos, you cannot see anything, nothing subtle can be seen at the full level. I mean, you may see something intermediate, but which you see in the pictures, but if you want the full semi-classical limit, he proves this unconditionally. Now, his proof comes from another idea, and I want to just tell you this amazing idea that goes back to Hillel Furstenberg. It's called homogeneous dynamics, and a rigidity feature that is critical in his proof. And so let me explain to you something very simple. It's called times 2 times 3. So if you look at the interval 0, 1, and you look at the map, x goes to 2x. That's a 2 to 1 valued, but if you look at the inverse image of a set, it's measure preserving. And there are many invariant measures which, I mean, x goes to 2x, basically you're studying the dyadic expansion of a number, which can be as complicated as anything in the world. Suppose I look at x goes to 2x, that's one transformation, and another transformation, x goes to 3x, which commutes with those two commute. Lebesgue measure on 0, 1 is invariant under both of those. So Lebesgue measure is not the unique guy invariant in either case, but what Furstenberg says is there's only one measure, other than trivial ones, which are invariant under both of them. Rigidity comes in. So if you look at something in base 2, and it's random or structured, then in base 3, you can't, the minute you make 2 bases, things rigidify. It's a fantastic conjecture of Furstenberg. It's not known to be true, but Dan Rudolph proved this conjecture many years ago. If you assume that the measure, which is invariant under T2 and T3, so we need at least 2 commuting transformations, at least one of them has positive Kolmogorov-Sinai entropy. If you have that, then you have the remarkable feature that the measure is Lebesgue measure. So there's this rigidity the minute you have a rank 2 commuting transformation. Now remember, we have this geodesic flow, we have this Hamiltonian, we just have this one guy that we invariant under. But suppose I could cook up another guy that commutes with this guy, and Lindenstrauss understood that you could get something from the Hecke operators as well, which is a p-adic analog, and get a higher rank action going there. And then he, together with his collaborators, I should show the slide, have a complete generalization of this Rudolph theorem. The only weakness of their work is that they need to know, in order to classify measures under higher rank, they need to know that the, what? That's not good. They need to know that that you have positive entropy for at least one thing, and that's a very strong condition, something that's not necessary in other works of Ratner, for example. Anyway, he was able to prove positive entropy by going back to the ideas that Rudnick and I used when we made this conjecture, and he and Bergen extended that and proved positive entropy and hence solved this problem completely. And let me tell you, so that's a complete solution in the arithmetic case, but there are 2 great theorems in the general case, which are not as strong, but are still striking. So Nalini and Tharuman, on seeing that work, showed that for every x of this type, arithmetic or not, any weak limit, any quantum limit, must have Kolmogorov entropy, Kolmogorov-Sinai entropy, at least 1/2. the Liouville measure has entropy 1, and if you could show the entropy was 1, then it's a Gibbs measure, it's unique, and that would give you the equidistribution. But you can, to get at least 1/2 was a tremendous insight, and I'm running out of time. It's a very brilliant idea with using, amongst other things, entropic uncertainty principle. So, of course, there's some uncertainty principle that's behind this, and then in the final minute, so her theorem resolved the long-standing problem. The first question that anybody asked on this was, could you have a weak limit which is actually the singular measure on an unstable periodic orbit? People were trying to make eigenfunctions built on these, and they could never do it, and the answer is you can't. This theorem shows, because any weak limit, that guy would have 0 entropy, and this has positive entropy. So this is already a tremendous progress towards the fact that any quantum limit must be very complicated. And then the most recent result involves a new uncertainty principle in quantum mechanics, called, in harmonic analysis, called the fractal uncertainty principle. This is due a theorem of Dyatlov and Bergin. I'll say in the words what it is in a minute. But here's a remarkable theorem. For every x gamma, take a quantum limit. It should be just Liouville. And this theorem says that the topological support of that measure must be full. So you can never leave out, you have to charge any quantum limit, must charge every open set positively. Can't, so this is a very quite complete theorem. It's weaker than the equidistribution, but it's already a tremendous statement about not being able to localize on fractal sets or anything of that nature. The source of this, since it's not involves, it involves some classical dynamics, hyperbolic dynamics, symbolic dynamics, something Michael mentioned, combined with a new fractal uncertainty principle, which says simply, let me just say it in this word, says that the usual uncertainty principle says that f and f hat can't be both localized, and there's a measurement of how close they can be localized. Well, if f and f hat can't localize on fractal sets of certain dimension in a certain quantitative way. And that fractal uncertainty principle, coupled with the classical symbolic dynamics, allows you to prevent, forces you to have full topological closure. So my whole lecture has been about the fact that if you have a fully chaotic system, all evidence is, and it's a theorem in many, many cases, and I think it's universally true as to how it happens, is that you just equidistribute at some God-given rate, and that you don't see the fine structures of chaos of the classical mechanics. And after all, the Schrödinger equation is linear. So why? It does smooth things out. Thank you.
Thanks, Peter, for a wonderful talk and taking us through, I think giving a completely new perspective, the arithmetic perspective, on things that we thought we understood. Questions? Okay, okay, Mani.
You cogently mentioned about observables and measurement.
Yes.
And in spite of all these sophisticated presentations they have kindly made, why is it that the measurement problem is still based on dry axiom, not derivable from a sophisticated analysis like you have done?
I don't think I know the answer to that.
Sorry?
I don't know the answer to that. All I know is that if you take the definition of observable as is customary with taking a classical observable, quantizing it, and measuring it in a state, then understanding it in an integrable system is very easy, or is understood, and in this kind of fully chaotic system, all you will measure is just random equidistribution. So I'm just telling you a mathematical fact. I can't say something philosophical about quantum mechanics, I'm afraid.
So every year new theory comes but one never goes away. So,
No. Okay, I'm just answering the question that I think many people were asking around this quantizing a chaotic and the Bohr correspondence principle. So I'm saying the Bohr correspondence principle, as was mentioned before, is a very singular limit, and at the level of solutions, it does not carry through, and you cannot see chaotic behavior in the semi-classical limit.
thank you.
Thanks. Was there a question somewhere else? Up there? There.
I was just wondering if there are sort of known generalizations of these ideas to non-Hamiltonian systems.
Yes, yes.
Both the correspondence principle and the other.
Well, I think, I don't know how to, you can quantize probably anything. I can only quantize Hamiltonian systems. Some people can quantize anything that moves. So a lot of these ideas do generalize, especially the semi-classical analysis. But the part that won't generalize at this point is this kind of very, the part that I'm saying is relevant in this analysis is this very structured other things like Hecke operators or symbolic dynamics that have to be very accurate in order to combine the sort of Ehrenfest time with the dynamics and marry them by some, which is what Nalini, I didn't explain, but that's what she's doing when she's computing entropy, estimating entropy directly. So a lot of it generalizes, but many of the techniques I'm talking about, the answer would be no.
Okay.
Yeah, we'll have that question and then Michael. Yeah, go ahead.
So when you quantize a classical system, so what happens to the chaos threshold, which sometimes appear like Km thresholds in the classical system? Does it carry over to your quantized systems? Because they do not have the symplectic structure, I guess.
No, this is all Hamiltonian, but when I start off with, and I'm nowhere near Km, so if I start off with a completely integrable situation and I perturb it a little bit, we'll end up in what Michael was calling a mixed thing.
Right.
And then these questions become very complicated. Some orbits will remain, and then this is well studied by Lazutkin and people like that. Like you have things like whispering gallery modes and things like this. But in a fully chaotic system, you don't have any invariant tori. They're only integral.
I understand. So do you have a quantum picture for this mixed situation?
There's a big industry of that. I have nothing to say.
Okay.
Michael.
So this is sort of halfway linear combination of a comment and a question.
Yeah.
It seems, from the point of view of asymptotics, what you've described is actually rather crude. The methods you need to prove it, of course, are not crude. You've described that very beautifully. But you know, as I mentioned, for example, for eigenvalues, random matrix theory is one part of the asymptotics. But if you look at larger energy ranges, but still semi-classical, you get different scalings with Planck's constant, and it's then non-universal in ways that you see level clustering that does correspond to periodic orbits.
Correct.
So when you say in the limit that you don't see any specific features of the ghost, of course that's correct, but you have to say which limit. And from asymptotics, we now understand different levels.
I agree. I'm always looking at what I view the harshest. So if I'm looking at zeros of zeta, I would be looking at local spacing at the local level. That's always the hardest, as you know very, very well, because the number of periodic orbits is exponential, and that method does not allow us to do anything rigorous. This allows us to do something rigorous on that problem by avoiding the issue of trying to understand the exponential you can always write down the answer on the universal cover and then sum over gamma and try and understand those sums. I've never been able to push through at this, what you're saying is crude, but I'm saying is the local statistics or the local behavior, and it's that that I've always viewed as the challenge. And
Yes.
that's where the universality comes from.
Indeed, but it was precisely the common feature of the breakdown of random matrix theory that led us to look at the statistics of beyond random matrix
Yes.
and see this.
No,
kind of-
no,
so that's
And the minute you go into the regime you're talking about, there are other methods.
and with eigenfunctions, of course,
Yes.
it's looking at the detailed local correlation, which tells you about the oscillations.
Yeah. So these formulae have been used to answer many, many questions of that nature. So the moral of the story is the eigenfunctions are automorphic forms, and the question is, are we asking a natural question in the theory of L functions? And that formula that I told you says absolutely, and it's the reason we pursued it. Usually, you might ask, well, this, and then you're asking something there, but here, this observable is the central value, and this is studied, this is the central theme of the subject.
Spenter.
Hi.
Yeah.
Great talk. You mentioned about this operator A, but as a mathematician, you must be having some definition of
Yes.
what type of operators you're working with.
Yeah,
in
so
these dynamical
there's little
systems.
a, which is a symbol,
Yes.
and there's a whole theory of pseudo-differential operators which allow you to construct an operator whose symbol is little a. That's a microlocal construction. It's not unique, but any two such operators that you make agree at zeroth order, and then the next term is lower order. So any question I asked is in the answer in the semi-classical limit is the same. So we have to live with the fact that there's no canonical quantization.
But I think maybe Spenter was also asking the class of functions.
No. So the observables, okay, are smooth. Now, in this world, we work with smooth functions. You want to put some discontinuous thing there, I panic.
So maybe I wanted to just ask something.
And by the way, the
else.
theory of pseudo-differential operator is developed up to smooth. Everything is integration by parts.
You know, in physics, we are always interested, I mean, many of us, in describing phase transitions, different phases, and in the context of black hole physics, where all this mixing and ergodicity comes
Right.
in, and there's a phase transition to that state.
Yes.
So in your mathematical formulation, is there some understanding of how the measure actually behaves? Gets
So on
across?
smooth, so the answer is very clean, that the op A phi j is the integral of A plus something which is very uniformly small, decaying like T to a God-given power, and we know the exact power. That's if I assume Riemann. And so we know what's true. And so we know exactly how much it smooths out, and then from there we can look for finer features. And if you look, I could start to probably see finer features, but that's secondary as far as I'm
I
concerned.
think Spenter, I think Peter's context is very much quantum mechanical,
Yes.
whereas I think you have in mind the quantum field theory.
Oh, yeah.
that's,
I'm talking about
But
1925.
in a sense that, no, just a minute. In the sense
That's
that
why you put me
I mean,
first.
the
I'm
type
19.
1
Yeah.
von Neumann. and the
type,
kind of,
I mean, in this simple system, can you see these type of features?
No,
Suppose-
so there's no, we don't.
Perhaps
see-
not,
Yeah,
actually.
we
That's
do,
probably-
we do see features which, so Berry has a conjecture that called the random wave conjecture, and we can show that's false in these systems, precisely because the arithmetic eventually will make some higher moments wrong. So it's why any conjecture you make, or any statement you make in physics that this system always has this property is almost never true. You can't make universal statements.
Nikita.
In Jacobi's way of integrating
Yes.
the geodesic flow and ellipsoid, he actually discovered what's now called the algebraic integrable system. So it's
Yes.
actually, it's a complex symplectic manifold, and
Right.
there are billion varieties, are level
Yes.
toric. So in this context, quite often in semi-classical limit, we find the use of trajectories which happen in complexified phase space.
Mm-hmm.
So in your case, your space actually has a very nice complexification because you just take SL to C mod gamma. So do you have any use for periodic
Absolutely.
trajectory? Okay.
many of the results which allow us to technically prove these theorems, which I didn't tell you anything how to prove them, involves taking this real Riemannian surface and taking a Grauer tube over it in order to see decay of certain. So in all these asymptotics, there's gamma functions everywhere. And a gamma function, okay, if you give me a second. The reason Riemann was so genius is he computed the first 3 zeros. And the reason that's so hard is there's a gamma factor in any formula. And so if the first zero is at height 14 point something, that's very high. You already got an exponential decay from the gamma function. And he overcame that by some Riemann-Siegel formula. The exponential decay in many of these formulae, which I haven't told you about in these L functions, makes it very hard to see the size of the observable without the gamma functions. So to get rid of the gamma functions, you complexify exactly what you say. You complexify this real manifold into a Grauer tube, and that tube is exactly as fat, just fat enough to cancel the gamma function. So the answer is absolutely. We complexify, and it's an extremely important tool.
So since Peter is only here today, I'll abuse my chair privileges to ask him one question on my side, which is these arithmetic surfaces that you said which had the Poissonian as opposed to the
All of them do.
So these are these the surfaces that also admit these belly maps?
No,
They're
no,
not.
no. Those aren't arithmetic necessarily. So no, they're arithmetic. They're not
Yes.
congruents. Yeah. So some of them are related.
Some of them, but
Absolutely,
not all
yeah,
of them.
Yeah. So those are ones that are defined over Q bar. These arithmetic surfaces are discrete, and so I think as I said, Bogomolny reinvented the notion of an arithmetic surface. He had 3 examples, and he knew that these were triangles. They tessellated the plane.
Yes.
And then he discovered what it is about the integers in the 2x2 matrices that generate or inside there, that they have some embedding properties in terms of number fields, which are a little harsher than what you're talking about.
Okay.
But all the arithmetic ones have the statistics, and it's numerically.
And the understanding for why?
Well, there are 2 ways to try explain it. One is that you got these commuting operators. That was the way I explain it. You can try use the trace formula, which is this periodic formula that is, in this case, called the Selberg trace formula, and in the Gutzwiller setting is more general. The trouble there is that what Michael says he proves is not rigorous. Okay, by my standards, it's not rigorous, so he will tell you that so what he does is he computes averages, and when he wants to throw away some terms, he throws them away.
But we all guilty of that here in this room. I think, so
He always gets the main term if it's not arithmetic, yeah.
That's, I think, where we physicists land on our feet. Okay, so great. Thanks very much again. And so let's thank Peter again.